enough.
Yes.
It would also be possible if we could prove that side CD is congruent to DE. That would be angle, angle, side. That would also do it.
Okay.
Not sure I see anything else, but that, I think that's all I've got here for this one. In terms of like, I think that's everything. So how are we going to prove the sides are congruent? I guess I want to ask you, have you done any proofs where you've said like AC is equal to AB plus BC?
Yes.
Okay. And then on the other side, we know that AE is equal to, let's go, AF plus FE. And then you can set them equal, but there's nothing that overlaps on there. So, so there's something I'm missing here to be able to prove that the triangles are congruent. Do you see anything that I have missed here?
Is it like the reflexive property?
So the triangles, none of the triangles share the same side that I can tell. Because the reflexive property would be like, CB equaling BC, but that nothing is shared in them.
Is it E and C are congruent? Or
Yes, those are congruent angles.
oh, maybe ED and CD and then CB and EF.
Well, we don't, so yeah, so there's not enough here. Like we would really like CB to be congruent to EF, CB to be congruent to EF, but there's not enough there to show that because we don't know their length. Now, this is a problem set A question, so there must be something very straightforward that is not being that I'm not seeing here, because these aren't meant to be very confusing in any way. So let me just quickly run through the notes here and see if there's something that I'm missing, because you could also prove that the triangles are similar, but that wouldn't allow you to prove congruence of them either. So is there something about CD and DE being congruent that would also really help?
I don't know. I'm not sure.
Yeah, I'm struggling here because I don't see the there's that one listen missing. So if let me go backwards here. If we could prove that the triangles were congruent, you would say that BDC equals FDE by corresponding parts of congruent triangles. So you could write up most of the proof without this. It's just that it's really useful to be able to do it with the triangles. So
Yeah.
I'm actually somewhat like shocked here that we can't figure this out here. It's always just something that's just not all that easy to see. So this adds up to that. AC congruent to, okay, well, let's move to another question here. I don't want to spend all our time on one proof that we don't get the full answer to. But do you see the path from the givens, like AC congruent to AE? You could talk about it being a isosceles trapezoid, which means those base angles are congruent.
Yes, I see.
Since angle CBD is congruent to DEF, that also allows you to, well, that's just another thing to help support the triangle. We're just missing that little piece that says that you've got to get a side congruent out of these things. Yeah. So one other thing that comes to mind here is that the altitude, which we don't know if it goes through D, of an isosceles triangle, it does make a 90-degree angle with that's kind of another direction to go on here, but I don't think that's the right step. So let's not do that. Okay, let's switch to a numerical problem just to get some better sort of a better feeling here for these. So let's kind of we talked about some formulas yesterday that I left you with, and start with those here. So it says the sum of the measures of the angles of a polygon is 1620. Find the number of sides of the polygon. So they're referring to the interior angle measure here. One reason is that this number is way bigger than 360. So if you remember that formula from yesterday, the sum is n minus 2 times 180, and they're giving you the sum. They're telling you the sum is 1620.
Right.
Do you have that formula from yesterday's notes?
Yes.
Great. Now, yeah, I mean, I'm sorry. This is really bothering me. We don't know. See, I think you can say that then that DE is congruent to CD, and that's your angle side for this one. Because in an isosceles triangle, it doesn't matter how you draw it. That altitude always goes through there on the bottom, and since those other angles are congruent, I mean, I think that's how it would go. I don't know. I guess I'll have to let that go. All right, I apologize. I didn't want to make sure you don't get. I don't want you to get stuck on the test.
It's okay.
All right. So this formula here, how would you solve for n? You've got 1620 equals n minus 2 times 180. What would you do to solve for n?
Distribute 180.
You can. That absolutely works. Like this here. It does make the numbers a little bit bigger. What would you do from here to solve?
Or add 360. But
Yeah.
for the first one, you could divide 180.
You could divide. Yeah, you get to the same answer. If you got a calculator, it does not matter what you do. You divide both sides by 180, and you get n equals 11.
Okay.
So that's kind of your standard question for this, so one type of problem where they give you the sum and you have to figure out the number of sides. And they usually don't give you a number that like means anything. Like what's an 11-sided polygon? I don't know.
Yeah.
Doesn't really matter. Now the next type of problem that's kind of the same type of problem is they give you the number of sides. They tell you, okay, it's got 33 sides. This time they want the sum. This is very important to distinguish between the sum and the actual angle measure. So they're telling you n is 33. The sum of the interior angles is n minus 2 times 180. So could you try solving this?
Yes. Um, 5,580.
What did you multiply should be a fairly, oh, I'm sorry, that is correct. I apologize. I thought the number was quite a bit larger. So it's 5,580 degrees. Okay. Now part B here asks for the interior angle measure. So it's like saying what does each interior angle equal? And the only way to do that is to take your sum here and divide it by the number of angles.
Okay.
So the number of angles, so you have to take that 5,580 and divide it by 33 sides. So we don't know what this thing looks like, but imagine it's got all these sides. So that's really bad, but you're just finding one of them. You're just finding you're just finding one of these angles here. And sometimes it doesn't work out nicely. That is the case here. I don't believe this is going to be anything nice. So when you have to round, you should round to whatever your instructor says to round to.
Okay.
Now, what did we say about the exterior angle sum? Now.
It's always 360.
It's always 360. Yeah. So the actual, I didn't tell you that everything here. Part B actually just asks about the sum of the exterior angles. The sum of the exterior angles is always, it's always 360.
Okay.
All right. So now let me give you another problem for this one. So this one says, if the measure of an exterior angle of a regular polygon is 15, how many sides does the polygon have? So sometimes it's good to draw a picture here. So the exterior angle, they're saying that one right there is 15 degrees. That means that the interior angle is 180 minus 15 degrees, which is 165. Okay, but you can actually use either one. So the exterior angle sum is always 360. If you want to know about the exterior angle, you divide by the number of sides, and that equals 15.
Okay.
So you'll see in a moment why this is the preferred path here. Could you solve this for n for us?
Yes. Um, 5,400.
N cannot be 5,400. You're just solving this equation right here. The 360 over n equals 15 over 1.
Oh, so do you? Okay.
Yeah, please ask your question. I mean, I don't want to just jump in and tell you how to do it if you're not sure, because I'd rather hear, hey, I don't know, or I'm not sure.
Do you like multiply by n both sides and then divide by 15?
Yes, that works. Yeah, so if you multiply both sides by n, the n's cancel, you get 360 equals 15n, divide by 15. Can you tell me what that adds, what that becomes?
24.
Good. Okay, now maybe that was, so I think the direction you were going was maybe working with this one over here.
Yeah.
So so this is kind of working backwards now. So so we know it's a 24-sided polygon, but let's see if we confirm that using the interior angle now. So the sum of the interior angles is n minus 2 times 180. But if you divide that formula by the number of sides, that gives you the interior angle measure. So this thing on the left here is, I think, one of the formulas I gave you last night to have if you
Yes,
just want
yes.
the interior angle. So in terms of how you solve this, just like you did in the other side, you multiply both sides by n.
Okay.
Okay, so that results in 180n minus 360 equals 165n. You subtract 165 from both sides, 165n from both sides. And so that leaves you with 15n minus 360 equals 0. Add 360 to both sides. And that leaves you with 15n equals 360. Wouldn't you know it, it's exactly the same formula as we have on the other side, but the answer is also the same as well.
Right.
So they work going either way. There's always kind of a shorter path to answering these things.
Right. Okay.
Just keep that in mind there. Okay, so I think I've given you all the like kind of standard questions about those 4 formulas. Is there anyone that you would like us to do another problem with?
Uh, no, I think I got it now.
I think you got it. Okay. All right. Okay. Let's look at a problem kind of like from last night. I think this is really similar, but actually we should do a proof now. I apologize. We should do another proof. All right, let's look at this one. Hopefully it's just works out nicely. Okay, so here's another proof for us to talk about. And you know, just you know, be fair that if you wrote down the steps from the previous one, I mean, you'd get most of the credit for the problem. I mean, that's the goal here is just, you know, get a good grade, show your understanding, and then, you know, you won't see this again. I don't think there's any proofs in the second half of this course.
Okay.
Right. So just keep that in mind here. So this one says angle S is congruent to angle ROP. So angle S congruent to angle ROP. Then angle ROS is congruent to angle P. And we're supposed to prove that angle SRO is congruent to PRO. But they say do not use angle side. So the reason is, that's probably the most important thing we should talk about with this problem. The reason is the order matters. So one of the things I can do here is like let me label this SRO. So I'm gonna draw ORP over here on the right, but then I'm gonna flip it. So I'm gonna make it so that it looks like this. So this is still R, but this is P and this is O. But now the angles sort of don't line up the way you want. I don't know if that's clear or not. Maybe the drawing's not good enough. But
No, I
like,
get it.
but yeah, but the idea is, let me do it in blue here. Let me do it in blue. So the first one, you have an angle. So your side would have to be this one here, R to O. And so if we follow that same path, it's the one with the single, then the single, and then the side would be the R to the P.
Right.
So that's why you can't use AAS. But we want to prove that SRO is congruent to PRO. So the idea here is like, hey, you can't just prove the triangle is congruent. Like normally you can, but you can't. So this one actually is not a triangle congruence problem. It's a no choice theorem problem. What do you remember what the no choice says?
I remember it, but I don't remember. Yeah.
So the way the no choice theorem works is if you know two of the three angles are congruent, then the other angle must also be congruent because, and the example they often give you is like the angle measure. They say, well, if S is like 30 degrees and O is 120 degrees, then R must be 30 degrees. And then the same thing applies down here.
Right.
And so with that, you can say, well, there's no choice because SRO and PRO, they're the third angle in each triangle. So this is actually a pretty short proof. Okay, so
Right.
let's get to it here. So the first thing you said you like to do, you like to label all the givens. All right, so from here, we need to somehow indicate that there's three angles in triangle, in this triangle over here on the left, or this one on the left here. We want to say that, well, I guess there's a couple ways to do it. We could say that the measure, yeah. Let me just go back and read the no choice to see exactly how it's worded. I'll snip that in as well. Actually, there's not much to say here. Let me grab it, snip it in here as a reminder. So here it is straight from your textbook. It says if two angles of one triangle are congruent to two triangles of a second triangle, then the third angles are congruent, no choice theorem. So there's literally like nothing to do in this problem. Because you've already said that the angles are congruent, the second one is that the angle you care about, SRO and PRO, they're also congruent by the no choice theorem. Let me grab those. Sorry, no, I'm scrolling around a lot. I'm trying to get the letters too. So this isn't much for a proof, we'll say. So good news is we needed to review the no choice for that. Okay, now that might help us go something back at problem number one that we looked at today. Yeah, so so we actually do not need to prove the triangles are congruent in this problem. Let me just refresh it, start from the beginning. Apologize. This will be the last time we look at this problem because we finally have the answer. But this is like to my point of why you said, hey, I start the proofs and I come back, because that no choice really answered it. So since AC is congruent to AE, that means that angle C is congruent to angle E. That's part of our proof here. It's given that CBD is congruent to EFD. And so why are the third angles congruent? Because of the no choice theorem.
Okay.
So while Matthew here, I mean, I don't know why, I guess I thought you were doing triangle proofs, but I guess you're beyond that. Is that possible? You've been doing those
Yeah.
before now? Okay. So they're not going to emphasize that as much. Now, it might be that your instructor gives you a problem where you use the no choice to then get an angle and a triangle that you need for congruence. But obviously I tried to overcomplicate this thing. Okay, so let's start out with some steps here. So they're the givens. All right. So the first thing though is because the two sides are congruent, you know that ACE is an isosceles triangle. So this is one of those like, well, I don't know if you can just jump to it. I would probably say that triangle ACE is isosceles with vertex A. And that's definition of isosceles triangle. Now, some instructors let you jump right to 3, which is that the base angles are congruent. This angle C is congruent to angle E.
Mm-hmm.
And sometimes they let you shorthand that a little bit. They say same sides, same angles. And they're essentially allowing you to go from 1 to 3. Does that sound like something your instructor is approved with?
I don't think we've done that now.
Okay. So then this is not quite right then. The reason the angles are congruent is because the base, it's the definition of isosceles triangle, the base angles in an isosceles triangle are congruent.
Okay.
So if you go back to our picture now, that's the part of the picture without the blue, but it's like, oh, I've got 2 of the 3 angles in the triangle. Doesn't prove that the triangles are congruent, just proves that the angles are congruent. That's the no choice.
Right.
Which I think sounds really bad. I mean, it's like no choice. Like I mean, the idea is that there's only one outcome, I guess would be a better way to say it. So
Right.
that's that the angles are congruent here. Angle BDC is congruent to FDE. Like that. And you're done. Are the proofs this short on your exams, or are they often longer than this?
Sometimes there's long ones and sometimes there's short ones. He puts like every now and then he has like 1 or 2 that are like there are like blanks on them and you like fill them in.
Oh, good.
Yeah.
That helps quite a bit.
Yeah.
Okay, so another problem for us to look at, it's very similar to one that we did the last night. It was that whole substituting for like an x plus y situation.
Right. Okay.
So we're gonna see how far we can get here in this problem using that. So again, I would recommend separating the triangles. Relabeling what you can that's given. Now this is from problem set B, so that it probably isn't going to be that. It's not going to be as nice as the ones we did, but we could probably still come up with at least how to work these. All right, so it says it says AB is congruent to AC. So that means that the big angle here and the big angle here are the same.
Right.
So that's pretty helpful because that we can call that, let's say we're going to call that X and X. We can say X plus 50 equals 180. And when there's just a single variable, it's probably good to solve for that.
Right. Okay.
So that means that 2x equals 130. So x equals 65.
Okay.
All right, now we have to assume that, sorry, this is freeze, just screen, just a little technology issue here. There we go. So then these base angles here, we don't know what they are. We actually have no idea what these are. They're different letters now. It's like Y and Z.
Okay.
So this is not looking good because we don't know this angle measure here, but we can say that D plus Y plus Z equals 180.
Okay.
So unlike the previous problems told you that like BD was like a bisector or DC was a trisector. Those were the problems we used last night. That was really helpful to figuring this out. But we don't have that here. But my guess is you'll get something like that. So what else? Do you see anything else in this triangle that comes to mind that you're like, okay, I can maybe write something on that?
Mm, no.
Yeah, it's not looking too good here. So the only things that come to mind for me is that if we were to label like this part right here, this angle between there and this angle here, like let's say but the problem is we're introducing new variables, but we can do that. So we can say like, let's call it U and V.
Okay.
What we gain with those is that U plus Y equals X, which is 65. And then similarly, we can say that Z plus V equals 65. So I generally don't like adding variables. I don't feel great about this, but I'm a little bit unsure how to proceed as well. So I wonder if angle D, oh, you know what? I made a huge mistake here. I apologize. So here's the mistake. I didn't look at the second given. DBC is congruent to DCA.
Okay.
And that will help out quite a bit here. So we do have to add another variable, but let's do it correctly here. So before we do these, gotta look at all the givens. So it says that DBC, so let me call that, I'll call that Y right there. That's the wrong place again. Boy. Okay, DBC is Y, and DCA, this is also Y right here.
Okay.
So this is very helpful to be able to work the problem here now. So we actually know now that this angle in here, because the whole angle is 65, this one down here is 65 minus Y.
Got it. Okay.
Now, if we look at that triangle again, so this one on the right here is 65 minus Y. The one on the left is Y. So now when we add up the three angles, D plus Y plus 65 minus Y equals 180. It looks bad. That's the idea. But what happens to the Y's?
They cancel.
They cancel. So you end up with D plus 65 equals 180. D equals 115 degrees. And that is the exact thing that you're trying to find.
Okay. Right.
All right. So I guess the lesson learned here is to really look at the givens. And because I was not looking at it correctly. 3 letters is just not as clear as 1 letter for me. So I mean, you really should go to the drawing and figure it out. Adding variables generally doesn't work. So just keep that in mind. Do you ever get these always, sometimes, or never questions?
We do, yes.
All right. All right, so here we go. So do you have kind of a actually, I'm sorry, let me not do it this way. Do you have a like a path that you take, or like a methodology that you use when you try to answer these?
Usually just like try and draw a picture for it.
Okay, that's good. I was thinking more in terms of the always, sometimes, or never. So keep in mind, an always is like a proof. I mean, you wouldn't have to make a proof, but that's really hard to do. That means that it always, always, always works. There's no exceptions. The
Right.
never means that it never works, obviously, but you might think, well, I wonder if there's something that I'm not seeing. Like you think, oh, this doesn't work, but then there's that one time it does work. So my opinion is that sometimes are actually the easiest, because if you can find one that works and doesn't work, and then I guess it's kind of up to you if you think always or never are there's sometimes related, because like they're definitions usually, but your
Mhm.
strategy is really good. An equiangular triangle is isosceles. So what does the word equiangular mean to you?
All the angles of the triangle
Are the
are
same.
congruent.
Yeah. Okay, so the question here is even though this is an equilateral triangle, is this also an isosceles triangle? And what you have to do is ignore the fact that it's equilateral, and just remember, what is an isosceles triangle? Well, if it has 2 congruent angles, then it is isosceles. So is this an isosceles triangle?
Yes.
Yes. So it's either always true or sometimes true.
Right.
And that's, I think, the hard part here is like, well, how do I decide between them? If it's sometimes true, you have to find one counterexample where it doesn't work.
Yes, right.
But every equilateral triangle has 60, 60, and 60. There's no exceptions to that. So is it always the case that 2 of the angles are congruent?
Yes.
Yes. All right. So this would be an always true type of problem.
Hmm.
All right, so let's look at another problem here. These are like worse than true false. It's like true false with a third option.
Yeah, these ones, it's always hard for me to decide.
All right. The number of diagonals in a polygon is the same as the number of sides. Okay, now maybe it's not clear, but you should always start with one that kind of feels solid to you. Or like, oh yeah, like, is this a polygon?
Right. Yeah.
Yeah, I'm asking you, is this a polygon what I've drawn?
Yes.
It is. It's got sides. It happens to have 4 sides. Polygons can have 3 or more sides. You got to be careful though. Like a triangle doesn't have any diagonals. in it. So like that wouldn't work.
Mhm.
That's also plays into this, but this one has 2 diagonals. Do you
Mhm.
see that? So when our always, sometimes, and never, well, it's either sometimes or never, because
Right.
we just found one counterexample. So that's the one other. I'm trying to show you a path to like work through these. So now, unfortunately, you need to draw another one here. This one has 1. I need to do these in a certain way. 2, 3, 4. This one has 4.
5.
Am I not counting right? 1. This one has 4 diagonals, but 5 sides. But it's better than having 2 for that one, right? Like
Right.
it's feeling. So let's look at a hexagon.
But it makes like a star shape.
Oh, I
It
missed one. I'm sorry. It does have 5. That's bad. That's another problem that you could potentially have, is you don't do it right. So see, it sometimes works,
Yeah. Right.
because all you need with sometimes is one that works and one that does not work. And I actually like those the best, because that you feel good. You're like, oh yeah, there's one that works. There's one that, like, you could go back to your teacher and say, look, this one works. This one doesn't work.
Right.
Okay, next one here. It says an exterior angle of a triangle is larger in measure than any angle of a triangle. So if it's not clear what that means, and sometimes you just draw a triangle, like a nice one, like a 60, 60, and 60. And here's the exterior angle, which is 120. Is the 120 larger than any measure of any angle of a triangle?
Yes.
See, so this one worked here. So it's either an always or a sometimes. So the
Mhm.
question now is, well, can we find one where it doesn't work? And what I'd like to do is I try to find the ones where it's kind of the other extreme, if you will. So like, imagine this is like 150 degrees, and now this is 30.
Mhm.
And we don't know the other 2 angles, but they can't be more than 30. So we'll may say like 15 and, or let's go 16 and 14. This one's not written well. An exterior angle of a triangle is larger in measure than any angle of a triangle. It's larger than these other ones,
Right.
but I mean, is it, this is, so does that mean, and I'm not sure, this is why this is a language thing. Does this mean that if it's bigger than just one, it's okay? This is one of those where I probably would lean towards sometimes, but depending on how this word right here is interpreted, it could be always.
Yeah. Yeah.
So I hope this has helped with sort of giving you a way to work through these problems without, because you can always get it down to 2 after you do one example. Maybe you've already been doing that, but it will help for that. So one last thing I'll tell you about, I don't know how much you've looked at this book, but I think every 3 chapters they do like a cumulative review. Yeah.
Yes.
So one thing that I've seen teachers do, is if you go to page, I don't know, it's either page 434 or 449, depending on you're looking at the PDF or the actual book.
Mhm.
Maybe it's the PDF. I don't know. I can't tell, but you might look at those problems, because sometimes the teachers grab them from there because students don't ever look at them. And you might try
Yeah.
working some of those that seem like they're related to this section, this chapter. Just to kind of have a heads up on how to do it.
Okay.
All right, well, that is it for us for tonight. Thank you for letting me help you. We will not be meeting tomorrow because we met today. So we're not scheduled to meet until next week. I guess you probably have a final next week, or is this it for you for the semester?
There's two parts to my final. There's the proof part on December 16th, and then the like multiple choice like equation part is on December 20th.
Okay, so you actually go into that week. All right. So we'll definitely be meeting next week. We can start reviewing for that, and then we'll figure out what we do for the following week to make sure you're all set up for that.
Okay,
All right. Thanks so much.
thank you.
You're welcome. Bye now.
Bye.